Hello, my name is Gabriel Ueda, and this is my Lab 2 video submission for Physics 2. So the experiment we were doing was throwing up a crumpled piece of paper and exploring the effect of drag force on projectile motion. It's one that's usually omitted when learning about trajectory because the force of gravity is much simpler to talk about, and it's close to the actual trajectory with objects that are relatively aerodynamic. However, this lab utilizes an object that isn't aerodynamic to demonstrate the effect of drag force in a more dramatic way. The experiment was throwing a crumpled ball and using the tracker application to track its projectile motion, both in its trajectory and its x and y velocities and x and y positions over time. The system includes the ball and the surroundings, being air. So these two graphs show the x and y positions by time. You can notice that they aren't exactly, the x position isn't exactly linear and the y position isn't exactly a parabola. It's a little bit, the x position is a little curved and the y position's not a perfect parabola. That is because of the drag force shown, and it will be modeled on glow script. So this is the glow script data, and the code, the b value, which is the drag coefficient, was found to be 0.57. The initial velocity was 1.33, 1.5 or 0.156, and 0, and the initial velocity was 3.53, 3.53, and 0. And over time, the b value, which is the drag coefficient, was found to be 0.57 through trial and error of matching the final position with the glow script final position. The glow script data is shown here in order going down: the y position versus time, the x position versus time, the velocity of x versus time, and the velocity of y versus time. And on the left side you see with no drag force, and on the right side you see with drag force. You can tell that the velocity has a curve in it for when there is a drag force, whereas when there's not, there's no curve, and they're all straight lines. The position of y is a normal parabola without drag force, and with drag force it's not a very perfect parabola. The reasoning for this, the drag force showed a significant effect on the trajectory when put into the glow script data, and just from the tracker data you could tell there was an effect of the drag force. The general formula for the net force is F net equals Fg plus F drag in this specific example, and the drag force, the reason that it's causing a nonlinear velocity and nonlinear x position is because the drag force counters the direction of motion and pushes against the motion, slows it down, and that is largely based on the air's density as well. And the area, the surface area of the ball has an effect on that too. In conclusion, the lab shows that the trajectory with added air resistance models the actual trajectory much more realistically than without air resistance. This is an extreme example because the ball has very low mass and is very non-aerodynamic, and so it doesn't allow for a very ideal trajectory, and requires a drag force coefficient that is relatively high compared to, say, a ball. Possible sources of error may have come from an inaccurate mass calculation of the ball, the tracker program, or limited data points. And this shows that in reality forces are much more complex than simple models can predict, and there are many forces that are at play just in the world. The time versus velocity graphs predict the models with and without drag. It does not show a terminal velocity. However, you can predict a terminal velocity with terminal velocity equations extrapolated from this data. And if the object were thrown straight up, it wouldn't reach the same height, but it would reach the ground at the same time, because the gravitational force and the drag force on the way down cancel each other out.